Syncing 3, 2, 1. Okay. Hello everyone. Welcome to our second advanced lecture. We will be building upon the ideas we discussed in our first day, and we'll start talking about how we might be able to answer queries when we have to deal with structures like trees. So today we're going to be talking about Euler-Tors and heavy light decomposition. Euler-Tors mostly motivated by the problem of like subtree queries. So let's say we wanted to query and update subtrees, and heavy light decomposition, an extension of Euler-Tors that allows us to answer path queries. So let's talk about Euler-Tors. Euler-Tors, the main motivation behind Euler-Tors is, imagine you had a subtree query. So let's say you had a tree and you wanted to perform either point updates or the maximum of a subtree, so maximum subtree queries. How might we do this? Well, we've already learned structures like range query structures that can essentially, if let's say this second one was find the maximum of vi over a range, we all know how to do that, right? So let's try to convert this problem into that problem. How might we do this? Well, one idea is consider how we traverse a tree when we run a DFS. When we run a DFS, the order in which we traverse the nodes, let's call that the DFS order. So let's say we enter a node at a time t, and we also store where we exit that node. Well, that means that for the entire time that our DFS is still within the subtree, we're still within that interval. And as soon as we leave this subtree, as soon as we stop visiting within this subtree, we don't ever visit any node within this subtree again. So this indicates to us that this interval of time from the time we go into the subtree to the time we go out of this subtree represents an interval where our subtree is quote-unquote active within our DFS. So how might we store this? Well, let's say we ran a DFS, like the code you see on the left. We store the time that we currently are at as like some sort of global variable, in this case, current time. And so time in would be essentially when you enter the DFS. So the first thing you do when you enter a node. And then time out would be essentially at the very end of the DFS, the time at which you leave the DFS. So how can we perhaps store this time, right? So like every time we visit the node, once we store the time where we essentially like clocked into our subtree, then we increment the time counter. We can append this to the end of our tour or our DFS order, and then we run our DFS going through all the children within for that node. And so I guess if you look at the code for a bit, this kind of intuitively tells you that the interval between time in and time out exclusive, or where time out is exclusive and time in is inclusive, represents the interval where our subtree is active. So let's look at an example. Let's say our tree originally looks like 1, 2, 4, like this, right? So we start our DFS at the root at node 1. And so the time at node 1 currently is time 0. So what happens is we record that when we clock into node 1. And so our time in for node 1 would be 0. And then as we process node 1, we increment the time, and now we move to its children. So let's move to child 2 first, as a DFS would do. And once we move to child 2, what we see is that our current time is now 1, and we're going to increment it to 2. And so as we clock in to subtree 2, we note that the subtree 2, its time in is 1, and then we go to its children. So this time, let's go to 4. So now we go to 4, we clock that our current time for 4 is 2, and we also clock that since there's no children for node 4, we also are exiting node 4 in this operation. And so when we exit node 4, we record that the current time after we've done all of our operations on node 4 is 3. So we record that the time in for node 4 is 2, and then the time out for node 4 is 3. So now we go back up to 2, and here we don't really do anything because we still have a child left to go, and so we visit child 5. And now when we're visiting child 5, again, there's no children, so we clock in at time 3, and then we clock out at time 4. So now when we go back to node 2, we've recorded all of our time ins and time outs for 4 and 5, which are 2's children. And so now we're done traversing for 2, and so we record that for time 2, we clock out at time 4. So now we go back up to 1. 1 still has another child, which is child 3. So we go to 3, we clock in at time 4, clock out at time 5, and when we go back up to 1, we clock out at time 5. So now, within this DFS, we filled out this entire table, and we have the ranges for which these subtrees are active. Let's consider a slightly more complicated, let's consider the properties of all of these time ins and time outs. So observe that every single node within the subtree is visited only within the interval time in to time out. So that means that the number of times we visit a node within this interval is equal to the size of the subtree. And so naturally that means that the time out minus the time in must be the size of the subtree. We also see that this the range for a single node that is like the parent of a node must fully contain the range of a node. And you'll see why in the examples I'll talk about in a couple of slides. So let's look at this slightly more complicated tree. What we see is that for every node, like for example for node 0, you see that it goes all the way from time 0 up to time 9 as its interval. And for time 1, similarly, it has an interval from time 1 all the way up to time 5. And so what we do is we can store all of these time ins and time outs, as well as assign every single node to a specific time. And so essentially what we've done is we've assigned every node to a very specific time. So time 0 corresponds to node 0. Time 1 corresponds to node 1. Time 2 corresponds to node 4, and so on and so forth. And so we can actually view the properties pretty nicely. Let's consider a single subtree, where in this subtree you have clearly 5 nodes, and if you see time out, which is 6, because remember we're inclusive on the left and exclusive on the right, so time out is 6. And if we look at time in, which is 1 plus the size, which is 1, 2, 3, 4, 5, is 6. So we can check that this equation holds for this node, and if you check, actually it holds for every single node. And if we look at node 8, for example, node 4's interval fully contains the interval for node 8, which is what we would expect, because node 8 is a subtree of the tree at node 4. And similarly, node 4's interval is fully contained within the interval of node 1, and node 1's interval is fully contained within the interval of node 0. So let's try to answer our original question. Suppose we just had a segment tree over the values that were in our tree, and now we wanted to do a subtree maximum, right? So now we would look at, for example, we wanted the subtree maximum of node 1, so we would look at the in time for the first node and the out time for that node as well, and we see that that range goes from 1 up to 6. So now what we can do is we can just use that to query our segment tree. What is the maximum among all the times from 1 up to 6, exclusive to the 6? And it turns out that's 18. And similarly, we can perform a node update similarly, where we can just figure out what time a node corresponds to. Let's say we want to update node 6, then we figure out node 6 corresponds to time 7. So at time 7, we just do a point update and change the 22 to a 27. Let's walk through a simple live demonstration of how this might work. So over here at the start, I've already gotten all the input, and the input for the tree that we've been looking at is on the right. So now what we want to do is, what? Zoom in. So now what we want to do is we want to basically find our DFS. So our current time, it starts at 0, which we set globally because we want this time to carry over through all instances of our DFS. So can someone tell me, let's say we want to find the time we go in. How might we do this? Can someone, let's say we wanted to clock, yeah?
It's the current time.
Yeah, so the time in for this node would just be the current time. And so now once we do this, we realize that now we need to increment the current time because we're processing a node, right? And now we want to append it to the end of our Euler tour. So we do tour.append of our node, which is u. Okay, so now we want to do our DFS. So remember, we need to keep our parent because our parent is within our adjacency list. And so now we want to recursively modify recursively traverse throughout the tree. And so how might we do this? Yeah?
We look at the adjacency list.
Yeah. So we've iterated through the adjacency list, and now what do we want to do here? Like what should be the next line? Yeah, so we go DFS of VU because U is the new parent of V. And now we can just simply find the size of our subtree by doing size of U plus equals to size of V. And now at the very end, we want to figure out what time we exit our DFS. So what time should this be? So time out of U equals, what time should this be? Yeah? Yeah, current time. And the reason why this is okay is because we're actually incrementing a global variable every time we iterate. So we're actually changing current time within this for loop. Okay, so that's nice. So now we can do our DFS, and we can actually perform a check to see if our Euler tour has properly been constructed. So first, let's print our Euler tour. So now let's go to input output and then run our code. And so now we see that our Euler tour has time 0 has node 0, time 1 has node 1, time 2 has node 4, and we can check that this actually matches exactly what we have over here. So time 0 again is it has node 0, time 1 has node 1, and so on and so forth. Okay, that's nice. So now let's check our intervals. So let's say we want to check that the size of our interval is the same as the size of our subtree. So let's iterate through every node. And now let's check, now let's print both the size of the subtree at that node and the size of the range at that node. So the size of the range would be time out minus time in. And if we do this and we run our code, then we can see that the times, these are the same on the left, which is the size of our subtree, and the right, which is the size of our interval, which is exactly what we expect. Now, let's output our intervals to see if we can see that the ancestors are the ancestors all fully contain a node. So to do this, let's output the time in and the time out. And if we go over here, we can rerun our code. And so now we see that, for example, for node 0, the time in is 0, the time out is 10. And let's actually look at our previous example over here. For example, node 8. So let's inspect node 8. So node 8 over here is 3 to 4. So that makes sense because it's a single node. It should only contain 3 to 4, where the 4 is exclusive. And now its parent, which is node 4, which should be over here. Oh, wait. Oh, it should be over here. And this makes sense because 2 through 5 includes 3 to 4. And let's check node 1, which is this node. So this 1 to 6 also includes 2 to 5 and also includes 3 to 4. So this is also good. And again, the parent of 1 is 0, which is 0 to 10, which also fully includes 1 to 6, which also fully includes 2 to 5, and so on. So this verifies the observations or properties that we observed with our Euler tour. Now I'll hand it over to Balint to discuss heavy light decomposition.
Wait, can I have speaker notes? Okay, whatever. Okay, hello everyone. So I am here to talk about heavy light decomposition. So, actually before I start, does anyone have any questions about Euler tour trees? No? Okay. So, Euler tours are pretty cool and they can solve a bunch of problems quite nicely. However, they have some limitations. So, for example, consider the problem where you are given a tree and every node has a value v of I. Let's say initially those are 0, not too important. And then we want to support updates of the following three forms. Add x to v of I, find the maximum of v of I in a subtree, and find the maximum of v of I over a path. And then the constraints are again like n and q are of like 10 to the 5, 2 times 10 to the 5 on that order. Now, Euler tour trees, as we just learned, they can support operations 1 and 2. However, they can't really support operations 3, operation 3 because the different nodes in a path are not consecutive in an Euler tour, only the subtrees are. So we will need a slightly different idea to solve this problem. However, we will see how this idea actually relates to Euler tour trees and how we can kind of combine both of them. Okay, so that is actually what I will do. I will describe a strategy / data structure that allows you to support operations 1 and 3, and then I will show you how to combine this with Euler tour trees to get a nice implementation which also supports operation 2. Okay, so one key idea is that any path in a tree, any simple path in a tree can be decomposed into two vertical paths. So a vertical path is just a path where like you start at a node and you only ever go up, like towards the root. And the way you do this is by just finding the lowest common ancestor of the two nodes between which the simple path is defined. So, for example, in this tree, if we have the path from 9 to 10, and we want to decompose it into two vertical paths, we just find their lowest common ancestor, and we have one vertical path going from 9 to 2, and another one going from 10 to 2. And, well, the reason this is useful is because the way we are going to approach our problem is we are going to take our tree and decompose it into a bunch of vertical paths, which we will call chains. The point is that, like, imagine if our tree was just a single chain. Like, each node has only one child and one parent. Everything is linear. Then our tree would basically be an array, and we could just use a segment tree to do these operations, because segment trees support point add and range maps. However, obviously, you cannot do this on an arbitrary tree. So instead, we will decompose the tree into a bunch of vertical paths. And then when doing a query, we will just find like the intersection of the path we are interested in with these vertical paths, and then do like a segment tree range query on that intersection. Now, what we care about with this decomposition is that the number of chains on any path from U to the root should be small. So the number of so the reason we only care about paths from U to the root is because, as I just showed in the previous slide, an arbitrary path can be decomposed into two vertical paths, and the vertical path is just like a subset of a path from a node to the root. So really, we just want to minimize the number of chains on any vertical path in our tree. And then we will store a segment tree at each chain, and that will allow us to do queries efficiently. So let's introduce some terminology. So we will call an edge heavy if it connects to nodes that are in the same chain, and we will call an edge light if it connects to nodes that are in different chains. So in this diagram, each chain is highlighted with a different color, and we call the heavy edges the ones that are actually highlighted. And then the cost of any path, the cost of any path, like the amount of time it will take to do like a range query on it, will be the number of different chains on that path multiplied by the time to do a single segment tree query, right? Because you're doing one segment tree query on every chain on this path. And the number of chains on this path is just equal to the number of light edges on the path plus 1, because the light edges are the only times you like change what chain you are on. And then doing a segment tree query will take O of log n time. So we want to find a way to make sure that any path from an arbitrary node to the root only contains a small number of light edges. Any questions so far? Okay. So to do this, we will use the following algorithm. Well, okay, so I guess like one observation you have to make is that when we are, let's say we will start at the root, and we will generally try to extend our chains downwards. So one thing you have to notice is that for every node, we can make at most one of the edges below it a heavy edge. So for example, if we start at the root node, we can either choose to make this node a heavy edge or that node a heavy edge, but we cannot make both of them a heavy edge because we said that like all of the heavy edges form like vertical chains. So the key observation is that the algorithm we will use is that if the subtree size of one of the children of this node is at least half of the subtree size of this node, then we will make the heavy edge point there, and we will make all of the edges light. And this is valid because we know that at most one of the children can have a subtree size that's more than half of the subtree size of the current node. Because obviously if you had two different children, both of them had subtree size greater than half the current node, then like if you add them together, you would get more nodes than are in the subtree of the current node, which doesn't make any sense. Do you guys agree with that? Yeah? Okay. So, however, this has the implication that whenever you go down a light edge, the subtree size will get halved because all of the pieces where you had the light edge, the subtree size there is at most half of the subtree size of the original node. But the subtree size can get halved at most log base 2 of n times, because at that point you just reach 1 and then you can't really halve anymore. So what this means is that on any path from the root to an arbitrary node, you will have at most log base 2 of n different light edges. So from the root to any node u, you will have log base 2 of n light edges. Does everyone agree with this statement? Or do you guys have questions? Okay. Actually, sure. Okay. Does someone want to tell me what will be the time complexity of a segment tree query now? Like if we have a path from A to B and we want to do like a range maximum query on it, and we have done this heavy light decomposition. We have partitioned our tree into a bunch of chains, and on each chain we place a segment tree that we can, and then that allows us to do arbitrary range queries on that chain in log n time. How do we calculate how much time it will do to do a range query from A to B? Yes?
It would be log squared.
And why?
Because the log times you need to query the segment tree times is log, so it's log squared.
Yes, exactly. So basically, okay, so first of all, we said that an arbitrary path can be partitioned into two vertical paths. On any vertical path, there will be log n light edges, which means like log n plus 1 different chains, but log n plus 1 is still O of log n. 2 times log n is also still O of log n. So what this means is that on the path from A to B, we will have something like 2 times log n plus 1 equals O of log n different chains. And on each chain, we will be doing like a single segment tree query, and that will take log n time. So our final complexity will be log n times log n is like log squared n. And then we will have to like combine all of these results, but that's cheaper. Right? Any questions? Or, yeah. Okay. Okay, so one simplification we can do that is just good is instead of making a node go to instead of making the heavy child always go to the subtree size that has size greater than 2, we can instead just make it go to the heaviest subtree size. And like the idea is, in our older implementation, we might have been like slightly wasteful. Like let's say we had this tree, not all of these have a subtree size 1, but this has subtree size 4, so none of them are greater than half of 4, so we would make all of these light. That's kind of pointless. We can afford to have one heavy edge, so why not just make it go to the node with the largest subtree. Now, this will not make the time complexity better. It will make like the constant factor maybe slightly better, but it's just like simpler to implement and a bit nicer to think about. But like obviously this will still have the same behavior, because if there is a node that has like a much larger subtree, then that will still be the heaviest one. So that's where we will draw the heavy edge. Or yeah. Okay. I am not convinced whether people are following or not, but I don't know how to check this. Does anyone have a specific part they would like me to re-explain, since I think I still have a bit of time? Yes?
Could you explain why there's log n light edges in them?
Yes. Okay, so what we do is, so we start at the root, and for every node, we just want to decide which of its child edges we will make a heavy edge. So you agree that if for every node we make exactly one of its like child edges a heavy edge, all of our heavy edges will still form like vertical chains, right? And nothing will go both up and down, and everything will still be a chain. Okay. So the way we pick this heavy edge is we just pick it to point to the subtree that has the greatest size. But the only thing we actually care about is what happens if there is a subtree whose size is greater than the subtree of the original node. So let's say this node is node U. This is, I don't know, A, B, and C. So what we care about is if size of A is greater than size of U over 2, then we will make the heavy edge point to node A. And then we are not really like adding a light edge to node A. We're only adding a light edge to all of the other ones. However, for all of the other ones, we know that size of B is less than size of U over 2. And then like same thing for C. Okay, so like one fundamental idea is that there can be at most one child whose subtree size is greater than half the subtree size of U. Do you agree with that? There can be at most one child whose subtree size is more than half the original subtree size. Yeah, because like, for example, let's say the original subtree size is 10. How do we split 10 into two different numbers such that like both are greater than 5, but their sum is exactly equal to 10? That's impossible, right? Okay, yes. So there will always be at most one node whose subtree size is greater than half the original subtree size. That one will get the heavy edge. We don't really pay a cost for that one. And everything else will get a light edge. And that's where like all of the light edges will come from. But what this means is, and then we repeat this for like all of the nodes in the tree. And then what this means is that, let's say we are going from top to bottom, or bottom to top, doesn't really matter. If we're going from the root down to a node, then every time we go across a light edge, the subtree size of the current node gets multiplied by 1/2, or like it will become less than 1/2. So we might start at 10. Maybe this one had size 3, and this one size 6, and this one had size 3. Because these have to sum up to 1 less than that. Yeah, because this one is also a node, right? Then if we go down here, it gets more than halved, and we can halve at most log base 2 of n times, right? Because we do n times 1/2 times 1/2, and so on. And at some point we will get down to 1, at which point you can no longer halve. Yes?
Okay, so assuming each node only has 2 children, because what if we just had like one node with 9 children?
So that doesn't actually make things worse. Because again, let's say we have 10 and we are trying to split it up into a bunch of different numbers. Even if it's like 4 different numbers, it's impossible to have more than one number that's more than half of 10. So even in that case, our assumption still holds. We make the heavy edge go to the only subtree that has size more than half of 10. And for all of the other ones, the subtree size gets more than halved. So it's still true that every time we go down a light edge, the subtree size gets at least halved. Does this make sense? Okay. Any other questions? Yes?
Could you explain again how we got the complexity log n squared?
Yes. So basically, so as I just explained, all of the vertical paths will contain at most log n chains. And the way our algorithm will work, which I guess I haven't explained too much yet, is that we will do one segment tree query on every chain that intersects with our with the path from A to B. And each segment tree query will take log n time, and we will do O of log n segment tree queries. So that's just log n times log n, which is log n squared. And for some reason we like putting the exponent there, but that's just notation. Does that make more sense?
Yeah.
Okay, no problem. Any other questions? Yes?
So you have using the example of the 10, you have 4 children.
Yeah.
Each of them are like equally sized. Doesn't that mean none of them are more than half the size of the subtree?
Correct. So if none of them have more than half of the size of the subtree, then we could just make all of the edges light, and even that will make our complexity correct. However, in practice, it's simpler to always just make the heaviest edge have the heavy edge, because like, why not, right? There's no reason not to have a heavy edge. So if none of them have a subtree size greater than half of the original one, you can choose it arbitrarily.
And also,
Yes?
why is it 2 times log n plus 1 on the from A to B? Why is it 2 times
Oh.
log n plus 1?
So that's because I said that any path can be decomposed into 2 vertical paths. And then what we proved is that on any vertical path there will be at most log n times you switch. So then if you have 2 vertical paths, it's 2 times log n times. But that's not important for the complexity, obviously. Yeah. Any more questions? Okay. Okay, that was good. It's very good if you are asking questions. That is the whole point of coming to a live lecture instead of just watching a recording, or like one of the main benefits. Okay. So hopefully now we have reasonable understanding of how we would do, of like how it might be possible to do these point updates and path queries. We haven't really gone over any implementation details, and we also haven't gone over how to do subtree queries. So here is where I want to make the connection to Euler tours. So you might have noticed that in an Euler tour, if we just look at like consecutive elements in the tour that are also adjacent in the graph, those already kind of naturally form these chain-like structures. Like the important thing we care about them is that they are consecutive in memory so that we can build a segment tree on them. And like the nodes are also in order. And we already have exactly that structure. So specifically the way this structure is determined is when doing the DFS, the first node in the adjacency list of a node will be the one that will be like directly after it. Right? For example, if we're doing a DFS on this tree, if it's always the node on the left that comes first in the adjacency list, then our tour will be like 1, 3, 5, then we will go back up, then 2, 7, 9, we'll again go up, then 8, 4, 6, and then we'll just go up one final time. And this already naturally forms the same kinds of chains that we want for heavy light decomposition. So the way we will implement heavy light decomposition is for every node, we will compute all of the subtree sizes using a DFS algorithm, so using one DFS, and then we will sort all of the node, like the adjacency list of each node, so that we put the heaviest, like the node with the greatest subtree size at the start, and then we will just run our Euler tour tree algorithm. And that will basically get us the decomposition we want. And then the advantage of this is now we will be able to do subtree queries as well. Because basically what we will do is instead of having like a separate segment tree on each of the chains, we will have one collective segment tree, and all of our updates and queries will operate on that one segment tree. And then like, if we're just doing path queries, this isn't really different because each like segment is given a distinct set of indices, so like they will never interact with each other. So it's basically the same as if we just made a separate segment tree for each path, right? However, when we are doing subtree queries, we can do the same kind of thing we did with an Euler tour tree, because now we notice that because again we still have the property that all of the indices of nodes in a subtree are in a consecutive interval, so we can just query that interval exactly like we did with an Euler tour tree. Questions? Okay, now let's get into a bit more details about how our algorithm will work. So so far I've given you like a high level overview of how the structure works, but like I haven't really told you what, for example, what variables you will actually store to be able to like represent this structure. So one important variable that you will store is like the head of each segment. So we define the head of each segment as just like the node that's closest to the root that has the smallest depth, and we will store a head array where for each node we will store the index of the head of the segment, which is just like the label of the node. And then like the point of this is when we are doing path queries, if we are here and we want to get up to the root, we will like query this range, and then we want to be able to like jump to the head of this segment so that we can go to its parent and keep doing our query. Okay, so now let's actually go over how to do like our path decomposition. Like we want to do a range query from A to B. How do we actually decompose that into only like ranges that are within a single chain in our decomposition? So, for example, suppose we want to decompose the path from the nodes 5 and 8. So basically what that means is we want to find like a list of the pairs of indices in the tour that we will want to query in our segment tree because they correspond to this path. So the algorithm we will use is in some ways similar to the LCA algorithm from yesterday, which should make sense because this algorithm will implicitly find the LCA. So what we will do is we will look at the two nodes and we will pick the one and we will find like the chain it's in, which is defined by the head of the chain, and we will figure out which of the heads is lower. And like, what is the point of this? Well, if we have one chain here, this is its head. These are the different nodes, and maybe we have another chain here, and then here are like the two nodes we actually care about. If we know that this head is lower than that head, then we know that this entire path will be contained in the path from A to B, because we said that like we decompose it into two vertical paths going up to their LCA, but the LCA has to be above there, because if the LCA was somewhere in here, then the head of B would have to be lower, right? Yeah. So we will always pick the node whose head has like the greater depth and is further down, and then we will simply add the corresponding range to our answer. So actually, let's pretend that this chain goes down even further. Maybe this is our entire chain. I should put the node label outside. This is node A, and this is like the head of the chain. Then we will find like the index in the Euler-Tour traversal of this node. And then also based on that, we can compute how many nodes there are on this path, on this like range or path or whatever. And then we will add that range to our answer. So, and once we are done with that, we will just move A to the head of this chain and repeat our procedure. So for example, in our example, we notice that node 8 has a greater depth than node 3, which would be the head of the orange chain. So we process that. We see that like this only has one node, so like obviously we just add the range corresponding to that to our answer. And the range is like the index in the Euler-Tour tree. And then we move like the node pointer up one. This time the two heads we are considering are the head of the blue chain and the head of the orange chain, which are 1 and 3. 3 has like a greater depth, so we process that. We again notice that like going from this path upwards, we have to include the nodes 3 and 5, which correspond to indices 7 and 8 in the tour. So we add that to the answer, and then we and then we move our pointer up one, or like to the parent of the head, and then this time we notice that both of our nodes are in the same chain, which we will know because they have the same head. So then we know we can terminate our algorithm, and the final range we have to add is just the one between the two nodes. So like the one from the higher node to the lower node. And then you will notice in this case we are not adding the entire like blue chain, because this part is not on the path. We are only adding the section between the two nodes. Okay. Any questions about decomposing the paths? No? Okay. And then you will notice that this actually allows us to calculate the lowest common ancestor of two nodes. And the way you do that is just in the final step, you simply pick the node that's higher up, and that's like guaranteed to be the LCA. And like the reason for that is because it's like kind of the first time that two paths that were going upwards merged, right? Like you started at A and B, and you were trying to find a path that's only going upwards, and at some point they merge, and that's the LCA, and that is exactly the node that's higher up. And then this is actually, you could consider this to be a better method of finding the LCA than the binary lifting algorithm that we learned yesterday, because the construction time is linear, assuming that instead of sorting by the subtree size, you just pick the one with the greatest subtree size. And this also only takes O of n memory. So on the other hand, the binary lifting had n log n construction time and n log n memory, whereas heavy light decomposition has n construction time and n memory, and both of them allow you to find the LCA in log n time. Okay, so Larry will give a demonstration of how to implement HLD. Maybe that will make some of the details a bit more clear, but I guess, do any of you have any questions about like the concept? No? Okay.
Okay, so let's dive into this implementation. So what we'll do is we first want to run a DFS to calculate the important values, like the depths, the the sizes, the parents, and that kind of thing. And so I won't bore you with the details. I believe you all know how to do this. I guess the important note about this first DFS is you want to get rid of the parent from your adjacency list so that it makes your calculations in the future a lot easier. Okay, so now that we've calculated all of these important values, we can actually perform our heavy-light decomposition. So what we want to do is we want to sort our children in decreasing order of their size. So here what I've done is I've iterated over every single node, and essentially all I'm doing is I'm sorting each child of that node by the size of that child in decreasing order. And so what this does is this allows the first node to be the node that has the biggest size. Okay, so now once we do this, what we want to do is we want to perform our Euler tour. So within this function, what we want to do is we want to keep track of the time we go in, the time we go out, and we also want to keep track of the head of the heavy chain that we were currently on. So for this first step, this is similar to our Euler tour, where all we need to do is time in of u equals t. And now what we want to do is we can set that. So let's say that v is this node with the highest size. So let's say v equals the first child. So if v is the first child, then the head must be a lot farther along the path. In fact, the head must be the same as the head for our current node, right? Because the head for our current node is the head of this chain, and as we extend this chain downwards to v, the head of v what must be equal to the head of u because they're on the same chain. But if this is not true, then that means we're essentially starting a new chain starting with v. So what we want to do is we want to set the head of v to just be equal to its head, or v. Okay, so now that we figured out what the heads are, now all we need to do is recursively do our DFS. So in this case, what we want to do is modify our time, and then at the end, we want to figure out what time are we leaving, and so this time is t plus 1. Okay, so now what we see is we've calculated our we've calculated our important values. Oh yeah, do you have a question?
No.
Oh, okay. Yeah, so now we've calculated all of our important values, and so now we actually are ready to compute the LCA. So in this example, as long as we're not on the same chain, we choose the node that's on the deeper chain, and then we move it up to the parent of its head, and then we keep iterating. And so this is similar to the LCA code that you saw over on the slides. So now let's say we want to answer the question that we posed at the start of the class, which is we want to do a point update, we want to do a segtree query, or we want a subtree query, and we want to do a range query. So, okay, so suppose we have the seg tree. This is simply the seg tree that I copied from our slides for day 3. So to initialize the seg tree properly, what we want to do is we want to assign the value of a node to the correct time, and then initialize the seg tree. So this is what this part of the code is doing. So now let's answer some queries. So let's say we want to do a point update. How might we do this? Does anyone have an idea? So, of course, we're going to be querying in our seg tree, right? So we're going to be, or updating in our segment tree. So all we're going to do is we're going to call seg.update. We're going to use the tree size as our initial parameters for our segment tree. The point that we want to update within our segment tree is the time for our node. So in this case, the time for our node is the same as the time we enter that node subtree. So that's time in of u. And then what we want to update it to is we want to update it to v. So this is all we want to do for our point update. So now for our subtree query, we can do a similar thing. we've computed the time we go into a subtree and the time we go out of the subtree. So our query is similar. Does anyone have the? Does anyone want to say what you do? Yeah.
You do query 1, 0, segment tree dot size. And then time in of view and time out of view.
Yes. Yes. And what this does is this queries over the interval over which the subtree is contained. Okay. So now let's query a path. So first, what we've done here is this is an important step, but what you want to do is you want to make sure that you're operating on the one with the lower head. And so once we've done this, all we want to do is we want to query the path from the head over down to u. So does anyone want to say how we do this? Yeah?
You do seg tree dot query 1, 0 to the segment tree size. And then you do time in of view and time in of head.
Yes. Although you have to be a little bit careful because the time in of the head, because it is higher up in the tree, will always be before the will be smaller than the time in of view. So you actually want to do this. And because our segment tree answers exclusive, we actually want to plus 1 at the end. And so we want to update our result with this. So result equals to the maximum of result that we have so far and this new query. Okay. So now that we've updated our result, we want to move u up to the parent of the head. So does anyone want to do this one? Anyone? Yeah? Yeah. So you basically just set u equal to the parent of the head. And now that we're done with this, this while loop basically ensures that now we're both things are on the same chain. So now we want to find the last section of our query where both things are on the same chain. So does anyone want to do this part? Okay, so we're updating the result equals to the maximum of the result we have so far, and then we're querying along we're querying along this chain, and essentially all we need to do is we need to find the time in of the smaller one and the time in of the larger one. And so we can just kind of do the minimum of the two time ins, so time in of u and time in of v. And then we can also do the maximum of time in of u, time in of v. And then because our seg tree is exclusive on the right side, we should have an extra plus 1 here. Okay, so now that we have this code done, we can actually test this code over here. So here we've generated a tree, and if we run the code, we can see that it outputs 16 for everything. And we can verify this because if we draw out the tree, we can see 2. So if we draw out this tree, our first query goes from 1 to 5. And this query, the maximum of 1, I'll write the values here, 1, 4, 16, 8, and 2. So the maximum of these is going to be 16. And then if we change 1 to be 16, and we want 3 to 5, our answer is still 16. If we want 1 to 5, again, our answer is still 16. If we want 1 to 3, our answer is still 16. So our code is performing as expected. Does anyone have any questions? Okay. If no one has any questions about this, this concludes our lecture. Feel free to start working on the problems, which will be posted shortly, and make sure you fill out the attendance form.